Okay, so we're gonna cover some preliminaries, mathematical preliminaries, okay? So what we're gonna do over the next 3 weeks is progress through this sequence of physical and digital manipulations that define the process of forming an image. And for each kind of step along the way, we'll have a clear mathematical description of what we mean, right? And so we're gonna start by defining radiation in the real world, defining that mathematically. We'll then just define our measurement device mathematically. Our imaging system is another term we'll use. We'll describe the process of digitizing that radiation mathematically. And then once we've done that, we'll define how we're then going to process that with machine learning mathematically. Okay. And so this class and next class, we're going to talk about continuous math to describe radiation, because it's important to really understand that, to then understand how it's digitized, right, into a discrete function. This class and next class, really next class, we'll talk about how we're going to model our imaging systems as black box shift invariant, right, transformations. But that will lead us into these ideas of convolutions and Fourier transforms. So if you've taken any signal processing, this should all sound really familiar. If you haven't, right, or a course on circuits, right, for example, it's all very similar, except now all our functions are two-dimensional instead of one-dimensional, but it's all the same tools applied to that function, right? If this all sounds new, that's okay. We'll go through it kind of carefully. It's not incredibly important for this class. It's pretty important, but if it's new to you, I hope you'll gain something from learning about it. And then, of course, we'll talk about digitization and machine learning, right? And so after we spend a couple weeks in this trajectory, we'll then really spend the next month learning about machine learning methods, right? We'll want to first cover how we get to what an image actually is before we talk about machine learning. Okay, so quickly, we're going to start from the beginning, but we're not going to dwell on it because this isn't a class about physics. It's more about images and how we're going to manipulate them once they're digitized. So to understand what an image is, we have to think about radiation, right? Radiation in general, I use that term because we're going to talk about different types of imaging systems here. Here I'm showing electromagnetic radiation that defines a broad, very large category of image formation. But there's also, like I've said before, ultrasound imaging, which relies on sound waves. There's MR imaging, which, yeah, anyways, I guess also is fundamentally electromagnetic. But there's more abstract ideas surrounding imaging besides just thinking of an electromagnetic wave. But this is a good place to start. So on the left are very short wavelength electromagnetic forms of radiation. So those include gamma rays and X-rays, right? So clinically, gamma rays are a big no-no. So we're not going to talk much about gamma ray imaging methods, although they are used in astronomy. X-ray imaging is all over the place, right, in the clinic, right? And so we have X-ray systems to image like the chest, for example, which are pretty common. They're used a lot in low resource settings in particular to capture a really good kind of understanding of what might be happening internally in our bodies. But there's also X-ray imaging in advanced modalities like computed tomography or CT. So CT uses X-rays, and those offer a three-dimensional picture of what's in our body, right? Ultraviolet also is, used to image in microscopy sometimes, definitely in like semiconductor automated optical inspection. There's a lot of ultraviolet-based microscopes. And then the main thing we're used to thinking of when we think of images is this little tiny segment here where we have a rainbow. That's the visible spectrum, right? So our eyes are obviously tuned to that, but our cameras and all these other imaging devices we were just talking about in the introduction are really mostly in this visible regime. Infrared is also hugely important in imaging. There's more and more cheap infrared imaging systems out there available for digital infrared imaging. And then we get into longer and longer wavelengths, microwaves, which are used for imaging, let's say, people walking around a room, right? Lower resolution imaging applications. And then radio waves. And so radio waves, yeah, are a little bit further down, but people form images with those too. So all of these are described by Maxwell's equations. It's pretty simple to take those 4 equations on the left. If you've seen them before, great. I hope you've seen these before. They're pretty important. You can take those 4 equations and combine them to get this very elegant, simple equation here, which is the second order differential equation. It has two variables of interest, right? That are being differentiated. The first, this upside down triangle, this NAMBLA or del squared term, it's a second derivative as a function of space. So it's saying, hey, the radiation E is spreading out across space a particular way. And this next term, the second order differential is with respect to time. So it's saying it's also spreading out across time a certain way. And those two things are happening synchronously, right? They're equated, or they're very similar, right, with this proportionality factor. So that equation, you can visually see, hey, it's the second order differential equation. So I need to take the derivative of this function E, right, which is representing the wave, this electromagnetic wave, and come up with the same thing, right, effectively, right? And so what do you differentiate twice and get the same thing? Well, I hope you remember from math, that's like sines and cosines. You can also do e to the x, right, is always e to the x as you keep going, but that one tends to blow up. So sines are better. And so sines become sines after differentiating twice, right? Sine goes to cosine goes to sine with a negative sign, but that's good because we have a negative sign there, right? So you guys are all kind of on the same page with me there. So a solution to this equation, not surprisingly, is a sine or a cosine, right? So this cosine is a function not just of space, but also of time, right? Because our free space propagation equation is a function of space and time, right? And so we have this cosine that's oscillating across space and time, right? And how it's oscillating, well, that's defined by a variable k and another variable omega. Not surprisingly, k and omega are connected to this n and c term, n being the index of refraction or index of propagation, which is just something that describes how the radiation moves through what's surrounding it. And then c is the speed of light, right? And so that comes directly from Maxwell's equations, which is pretty amazing. So we have this oscillating function u that's defining radiation that's hitting, let's say, my dog or me, right, before that radiation's entering your eye. And we'll treat this, as a wave. And so generally, from the fundamental principles of imaging, the radiation that is forming the image is wave-like. There's interpretations to then get to this kind of picture of rays, which you've maybe seen in ray diagrams of images being formed. There's a way to kind of bridge between those two. But really at the fundamental level, all of imaging effectively is wave-like and relies on waves. That wave will then enter some black box system, right? And we're going to define this carefully. So this black box system is going to take that wave, let's say that has hit my body and then is going to reach your eye, and transform it, mathematically transform it. It's going to take the wave as one form and map it to a different form, right? And so that black box transformation can happen in a cascaded fashion. So there can be one black box that defines how the wave leaves my body and travels to the surface of your eye. There's a second black box that says how that radiation is shaped by your eye. And then a third that says how it transfers from the surface of your cornea to your retina, right? And so you can begin to put these black boxes together. Each one has an associated equation that defines the transformation, right? Luckily, as we'll get to, these transformations become, under a number of assumptions, very, very simple, mathematically extremely simple. So simple that you can just model them with one line of code in your computer, right? But we're going to figure out why and how that's the case. Okay. So this idea of a black box, it's a well-known idea that can be applied not just to signals in a circuit, it can be applied to images. So like I said, we can cascade these boxes together and define a sequence of operations that map radiation from one plane to another, where the quantities that are being manipulated define how the radiation is transforming physically as it moves through the world. Okay, and so we can make a bunch of simplifications. So we're going to forget about time in this class, pretty much. It's way easier to just remove it, right? So first, for most radiation, the time scales of this oscillating term omega are very rapid. So for light, it's 10 to the 14th hertz, right? It's incredibly fast oscillations that we don't really care about. Of course, things are also changing in the radiation as I move around, right? At a lower time scale, at the scale of hertz, right? And so we can capture that, but you just need to click record on your phone and capture a video, right? And so if we do want to include time, generally we'll think about time in this class as a sequence of images, right? Just each one captured at a different snapshot. This omega t term is describing the time scales of radiation wiggling, which are generally much faster than what we care about. So I'm not saying like just you could always neglect it, but for this class, we'll kind of just put it aside. And some other simplifications we'll generally use are, instead of writing a cosine all the time, we're not going to write it down because we're going to use complex numbers. So hopefully you guys are aware of complex numbers. I'll review them for the next slide, and then hopefully everyone will be on the same page because it might be a little rusty for some people. It's really a way to subsume this cosine term into a single variable. So this amplitude and cosine term we can write as a product of some amplitude and this e to the I k times r, right, which is a complex term, which is a cosine and I sine, which then we say is u. And then whenever we want to define our actual a cosine r, we just look at the real component of u, right? And then we've recovered what we're interested in, and then we no longer have to write cosine da 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 cosine da 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 cosine da da da, because that gets really annoying. We have in complex numbers a real and imaginary term, right? The way I think about complex numbers are simply as a two-dimensional plane where the x-axis is the real component x and the y-axis is the imaginary component y, and any complex number sits somewhere in that plane. And then really what's of interest in wave analysis is this amplitude and phase term. That's the polar coordinate representation of this complex number, right? So polar coordinates, remember there's r, the distance to the point, and then the theta from the x-axis at which that vector needs to be tilted to hit the point, right? And so really the amplitude is defined as that r term. R is it's the square root of the x and y term squared. It's that distance. And then the theta term is the inverse tangent of y over x. It just defines the angle of this blue vector there, right? And so really, it's hopefully not too surprising to see this type of representation. Any point on our field is represented by a, in space, is represented by a point in this 2D plane. And it has this particular amplitude, which defines how strong the field is. And then a phase, right? The phase is also kind of where it is in its wiggling, so to speak. I really encourage you to get comfortable with that if you are going to think about images, because it's a very easy picture of an image, right? If you say, hey, I have an array of numbers that defines the radiation somewhere, those can be complex valued, where the amplitude defines how bright the radiation is on that plane. And then if you need to account for the wave-like nature of that radiation, each pixel also has a phase, right? This value theta, which defines where the wave is oscillating, in its oscillation rather, at that plane. And we'll return to this again later, but we'll just be still writing this term u of r, right? Radiation as a function of space, r being anywhere in space, where we just now know it's a complex number. And then the third simplification is we're not going to have 3 dimensions always. We're mostly just think about 2 dimensions. And so what we need to get comfortable with is when images are formed, or when images are being formed, they go from plane to plane, right? So radiation hits me, step 1. I'm a plane. I'm not that thin, but I'm going to be treated as a plane in our class. Step 2, radiation goes to the camera lens, right? The camera lens we're going to think of as a plane. Step 3, it goes through the camera lens to the other side. Again, it's at a plane. Step 4, it goes to the sensor. And so each of those takes a 2-dimensional matrix that's defining the radiation, and then makes a new 2-dimensional matrix, and a new one, and a new one, right? That cascade of operations are going to be each one a black box. And that's really how everyone, I would say, kind of tries to distill things to, when they're distilling things to the simplest case in the world of imaging, that's where you want to get to. Because if you're able to get there, then things become pretty simple. You're able to utilize some of these tools I'm going to show you. Right? And so we're going to kind of always assume we're there in this class, just to keep things simple. Of course, yeah, the world is three-dimensional, and we need to account for my three-dimensional shape when considering how radiation might hit me and go to your eye or to the camera, right? But for the purposes, right, we can make some assumptions and say that's not the case, right? Or of course, right, things are changing and moving, right? But we're not going to consider that time component right now. You might in your final project and want to consider videos and how videos can be manipulated, but we'll kind of put that to the side for right now. All right, so what are some of these black boxes? So they can really be anything, right? But here's some simple physical things that can happen to radiation, to light. It propagates, right? It always goes through space and spreads out. It can diffract. It can hit a grating and spread out, right? It can focus. It can hit something and start to bend towards some center. All of these we can define mathematically. And those in turn define the properties of this black box, right? And so really what it is at the end of the day is it's a transformation T, right? That takes one two-dimensional array of numbers at the input, I, and makes a second one at the output, right? And so these transformations we are going to get really comfortable with because they happen physically to change radiation into different shapes and forms, and they happen digitally. We're going to be applying them to two-dimensional arrays of numbers, right, in our neural networks as we get to them.